Okay, and now you can see we made it. We're on the border, United States and Canada. As far north as we're gonna go. But we're not at the end of our journey, because there's one more thing I want to show you that's up here at the border, and it's at Grand Portage State Park. So, today we're going to talk about abstract data types. Abstract data types are tools that we use to solve common problems in computer science. It's surprising how few of these we really need to know well to solve most problems in this world. Containers, lists, and stacks are the three that we'll talk about today. In the next lecture, queues, trees, tables, and graphs will be addressed. But let's talk about the first one, containers. We've been implementing the bag ADT. That's an example of a container. It's a data type that you put things into and take things out of. Many problems are solved with such a simple data structure. Lists are another simple data structure. An awful lot of problems in this world are just simply maintaining lists of things, adding to the list, removing from the list, and so on. We can implement the list ADT, or abstract data type, concretely in several different ways, with arrays or with linked lists. But today we're just going to talk about the theory behind them, and not spend so much time on the exact implementation. A third ADT, the stack ADT, is really interesting, and we'll spend some time on it today. It uses operations called push and pop, allowing you to put data into the structure or take data out. The last thing you put into the structure is going to be the first thing that comes out. Here's how it works. We have an item. We want to store that, so we put it on our stack. We say we pushed it onto the stack. Now here's another item. We push that on top of the first one. Now here's the third item. We push that one on top of the second item. Eventually we're going to want to start to remove things. Removing is called popping off of the stack. So we push things on, we pop things off. The one on top is the one that goes off. That was the last thing in. It's the first thing out. Once that's removed, the second item comes out, and once that's removed, we can pop out the first item. You may wonder how you would ever use this data structure. It seems so bizarre, but in fact we use it all the time. In computer science, we oftentimes write programs that have functions. This means that they have to navigate between themselves. The main function here calls function 1. It has to know how to get to function 1, and it has to know how to get back. So the main function, when it leaves, builds something called an activation record. It's a list of exactly where it is in the main function, what everything is set to, all the information you need to get back there, and it pushes that on a stack. Now we're off to function 1. Function 1 is calling function 2, so as it leaves, it builds its own activation record and pushes that on the stack. Now we're off to function 2. Function 2 performs its tasks, and it's asked to call function 3, so it builds an activation record and pushes that on the stack and then leaves and goes to function 3. Now function 3 executes. It does everything it needs to do, and it's finished, and now what's supposed to happen? Function 3 wants to know where to go, and it goes to the stack to get that information. It pops off the activation record on top, and that tells it how to get to function 2. Function 2, when it finishes, pops off the top record, and that tells it how to get to function 1. Function 1, when it finishes, pops off the activation record that's there, and that tells it how to get back to main. We use the system stack very commonly in every program we write that has functions. Here's another example, very different from mathematics. This is called postfix notation, where operators come after the operands. We can resolve an arithmetic expression like this. We push on values and pop off values when we get an operator. So here we pushed on the 5 and the 6. Now we hit the operator addition. Addition requires 2 values, and so we go to the stack and pop them off. We complete the addition process, add them up, and once we've finished, we push the result back onto the stack. The next thing we hit is the value 3. We push that onto the stack. After that, we'll hit an operator, multiplication. That requires 2 operands, so we'll pop 2 operands off of the stack, the 3 and the 11. We'll do the multiplication, and we'll push the result back on. And now we've resolved the expression. We oftentimes use stacks in other ways as well. In a game program, you might have a mouse running through the maze, and it could get stuck in a dead end where it has to backtrack its way out. In this case, the mouse is doing fine, but if it started out going up instead of down, it would have had to backtrack. How do you do that? You put all the grids that you've been into on a stack. You push them on one by one and you pop them off to get to back up. There are many examples of stacks in this world. We've seen how they're used for function calls, for arithmetic expressions. They're also used by compilers, things that have to check parentheses. And, of course, recursive backtracking, which is what the mouse was doing when it was trying to keep track of where it had been. Tomorrow we'll examine a few others, but for today, thanks for watching.